Master Program, Faculty of Medicine, Public Health and Nursing, Gadjah Mada University, and distinguished participant, especially from the Ministry of Health of Indonesia. I see many people here also, and from the National Research and Innovation Agency, and also from some university and our colleagues from the pest control and the others. So I'm delighted to welcome you to today's guest lecture featuring Professor Tom Burkot. Today's discussion is particularly timely as we delve into the crucial topic of human as a driver of change in mosquito vector distribution and behavior. So, first of all, I would like to introduce Professor Tom Burkot. Hello, Tom. How are you?
Hi, I'm good. How are you? Thank you.
Okay, thank you, Prof. Okay. Professor Tom Burkot is a distinguished expert in the field of vector biology and control, with extensive expertise in vector-borne disease transmission and control spans over 40 years, focusing on disease transmitted by mosquito and ticks. His educational background includes a PhD in biology from the University of Notre Dame, USA in 1976, MSc in entomology from the University of Wisconsin, Madison, USA in 1978, and PhD in medical entomology from the University of Wisconsin, USA in 1981. Throughout his career, Professor Tom Burkot has made significant contribution to the field. He is recognized as a specialist in the transmission and control of the vector-borne diseases caused by protozoa, helminth viruses, and bacteria carried by mosquitoes and ticks. And Professor Burkot has developed and delivered course and training aimed at a vector-borne disease specialist, contributing to professional and technical education in the field. His communication skills are evident through the publication of more than 170 peer-reviewed papers on vector-borne disease and over 100 seminars, invited presentation, and key lecture at various training courses and professional meeting. His insights are not only academically profound, but also hold practical implications for public health strategies worldwide. As a note, Professor Tom Burkot is the inventor of ELISA method for confirming malaria vectors. So please join me in extending a warm welcome to Professor Tom Burkot. Without further ado, let us begin our journey into understanding the complex dynamics of mosquito vector distribution and behavior. So Tom, the floor is yours. Okay.
Thank you, Tree.
Okay.
All right. Can you see my slides?
Yes.
All right. First of all, thank you. I want to thank you for this kind invitation to be able to talk to you today about how human behaviors act as drivers of change in mosquito distributions and their behaviors, and how this oftentimes has impacts on the transmission of human pathogens to people. Now, let's see. Now, I want to talk about, before we get started on the main topic of today's lecture, which is about drivers of change in mosquito populations, I want to start out by giving a little bit of essential background to make sure we all start our discussion with the same sort of basic understanding. So I want to talk about the importance of mosquitoes as vectors of human diseases, with a particular focus on Aedes and Anophelines. I want to spend a couple minutes just on mosquito behaviors and mosquito life cycle, and before we get into what I call the mega drivers of changes in mosquito populations. I think there's a lot of people who probably are unmuted because we're getting a lot of background noise.
Yes.
Okay, and then we're going to talk about some drivers of change, what I call mega drivers, the mega trends of changes that drive changes in mosquito populations. And these can act on local, regional, or global, and this includes human-mediated transport, so human-assisted transport of mosquitoes, climate change, which of course everyone is very interested in these days, various examples of land use change, such as deforestation, agricultural development, urbanization, and also mosquito control, which is a major driver of changes in mosquito population. And then I want to end by talking a little bit about what we know that we don't know. And there's a lot of things that we don't know yet, which is a particular focus on some of the work in my group recently. So hopefully this slide is not everyone's familiar with, and basically it makes the point that despite all the publicity that sharks and crocodiles get, they're really minor importance as far as being the world's deadliest animals. And mosquitoes are responsible for killing more than 700,000 humans every year, more than any other animal, including humans. And about 608,000 deaths are attributed to malaria in the year 2022 by the World Health Organization. And also this includes enzootic malaria or monkey malaria transmission to humans, and about 40,000 deaths from dengue, according to the CDC. So dengue and malaria are responsible for about 90% of the fatalities by vector-borne diseases in any given year. Now, hopefully everyone is familiar with mosquitoes' life cycle. So we're going to be talking about mosquito behavior. So this slide encapsulates the dominant vector behaviors as we know them. We have start right here. We have oviposition, so laying of eggs, and then we go through the immature stages.
Sorry, maybe Mas Abdul, can you mute your speaker? Yeah. Okay. Sorry, Tom. Go ahead.
That's okay. So we're going to talk about a lot of these behaviors that are impacted by these drivers. So we have the adults emerge from larval habitats. Mosquitoes, of course, fly. They mate. They take sugar mills. The females blood feed, and then they rest and lay eggs, and so on. So, of course, a mosquito life isn't linear, but it's circular. And I think that that's an important attribute, that these behaviors are repetitive behaviors, that we go through egg laying, sugar feeding, host seeking, blood feeding, and resting, and over again. The only exception to this circular behavior pattern is mating. And that's actually pretty important for some of the changes in mosquito distributions that we'll talk about shortly. And mosquitoes generally mate only once. And then after they mate, there's a hormonal and a physical barrier to further mating activity. So they mate once for the most part. There's a few exceptions. Some mosquitoes, a small proportion, will mate more than once. But basically, that's the only part of the mosquito life cycle that doesn't repeat itself, or at least for the female mosquito. Okay, so when we talk about what is it that we talk about vector? So what do we mean when we say a mosquito is a vector? And it basically has to have two major attributes. It has to be competent, and it has to have capacity. And these are two terms that get, I find even medical entomologists who have been working in the field for a long time confused. And so let's just take a few minutes to talk about what does it mean to be competent to be a vector. And vector competence basically just refers to the innate susceptibility of a mosquito to become infected with the pathogen, to allow the pathogen to multiply and develop inside the mosquito body. So the mosquito goes from becoming infected when it first ingests the pathogen to becoming infective or infectious when it has the pathogen in the salivary glands. So that's competence, just the susceptibility of the vector to the pathogen. And this is some of the example in a malaria parasite. Not only do you get multiplication of the pathogen, but you get developmental changes. So hopefully this is, everyone's familiar with this slide, where the mosquito takes in a blood meal, takes in the sexual stages, the gametocytes, you get exflagellation in the mosquito stomach, fertilization to form the zygote, development of a mobile ookinete, which penetrates the mosquito gut wall, development of the oocyst on the outside of the mosquito gut, inside which sporozoites develop. The oocyst ruptures, the sporozoites make it to the salivary glands, from which the mosquito is now infectious. So that's all part of the innate susceptibility of a mosquito in order to be a vector. Now, we're going to spend most of today, I think, talking about vectorial capacity, and that is the behaviors that determine whether a competent vector, a susceptible vector, will become infected and live to be infectious and transmit the pathogen to a susceptible host, okay? So this is basically, is oftentimes defined in terms of three major attributes, behaviors, and bionomic characteristics of mosquitoes. First of all, you've got to have, it helps to have a lot of mosquitoes. Okay, so mosquito numbers, the frequency of biting on humans is an important attribute to bring the vector in contact with the human who may be infected. So the uninfected mosquitoes bite the infected hosts. They have to, so that's transmission of the pathogen from people to mosquito. And the mosquito then has to live long enough time for that pathogen to go from infected to infectious. The infectious mosquito then bites another person, and that person then becomes infected. Okay, so you got human blood feeding has to occur twice. So there's actually, when we talk about mosquito, when you talk about transmission of a pathogen, we're actually talking about two separate events. You have transmission to the mosquito, and you have transmission to the human in this case. We talked about you have to have it helps to have a good population of mosquitoes, so you have a high frequency of feeding on humans, and the mosquito has to be long-lived. It has to be able to survive long enough to go from picking up the pathogen to transmitting the pathogen. Okay, and that period of time is known as the extrinsic incubation period. So it's that period of time from acquiring the pathogen, and for malaria, be picking up a stage 5 gametocyte, to going through the developmental stages until you get the sporozoites. And for malaria parasites, that can be anywhere from a week to 30 days. Arboviruses is generally 1 to 2 weeks, okay? So when we talk about dengue and human malaria transmission,
berapa cair Januari, berapa cair Februari?
it's a fairly simple cycle in many ways. There's complexities in it. Again, you've seen this slide before. Uninfected mosquito bites the infected host. The infected human. The mosquito acquires the gametocytes. It has to then live through the extrinsic incubation period to become infected or infective. That mosquito then bites another a susceptible uninfected human, and the human becomes infected with malaria, and then the cycle continues. Okay, so that's dengue and human malaria transmission. So we also have this scenario, and it's something that Pak-Tri and I have been working on quite a bit, and I'm going to steal some of Pak-Tri's data later on as part of this lecture. And that's zoonotic malaria transmission, or infection of humans with the monkey malaria parasites. And it's actually, there's some significant differences from infection of humans with the human malaria parasite. This part of the cycle is the same. You have the uninfected mosquito, feeds on an infected monkey. It goes through the extrinsic incubation period to become infectious, and it then can feed on another monkey. If that monkey wasn't infected, then it'll become infected. And so you go through this cycle here. Now, the difference is, there's two critical differences. One is sometimes that infectious mosquito feeds on a susceptible human. and that human then becomes infected. But what's really different from the human malaria cycle is you don't see, there's no evidence for long chain transmission of people infecting mosquitoes, which then infect people, which then affects mosquitoes, that then infects people. So you don't get that long chain of transmission of person to mosquito to person to mosquito transmission. So basically, everywhere that we see simian malaria parasites, it really requires the presence of the monkey host, okay, the macaque host. So that's a critical and important difference. And why should we be concerned about zoonotic malaria? Well, there's a lot of reasons. First of all, it's a serious disease. It causes severe clinical illness. And it also is a threat to countries being certified as having eliminated malaria, because the World Health Organization has decided that if there are more than 10 human cases of simian malaria, then that country will not be certified as having eliminated malaria in their country. So that's a threat to malaria elimination to, I think, almost all the countries in Southeast Asia, including Indonesia. And I think the more we look for simian malaria parasites, the more we find it. So today we're really going to focus a lot on dengue, human malaria, and simian malaria parasites. So let's talk about some of the drivers that affect human behaviors that drive vector distributions and changes in vector behaviors. And the first thing I want to talk about is human assistance to mosquito movement or distribution. Now, the classic example of this is when we look at Aedes aegypti, we look at the dengue vectors, Aedes aegypti and Aedes albopictus. And both of these mosquitoes are vectors of dengue, Zika, and chikungunya viruses. They both have desiccation-resistant eggs, which means that the eggs can be laid on a container. They can become dry, and they will hatch later on when they're flooded with water. They both have relatively modest flight ranges by themselves. They only fly 100 to 200 meters under their own power. Differences are Aedes aegypti, we say it's a domesticated mosquito, so it primarily lays its eggs in containers that are made by humans that we provide for them. And aegypti likes to rest inside human houses and to hang around houses, whereas albopictus is oftentimes referred to as an outdoor or bush mosquito. So it likes to take advantage of things like empty coconut shells to lay their eggs, or tree holes and so on. But they also will take advantage of man-made containers to lay their eggs. Now, this is a map in a review by Tom Swan, who was in my group, and it shows where Aedes albopictus originated in Southeast Asia. And the thing I want to call your attention to on this map is you got the color coding here. The darker blues are areas in which the mosquito has been there longer, and more recent movement is in the lighter shades of blue. And one of the things, if you study this map, you'll see that these mosquitoes, Aedes albopictus, oftentimes travel to get great jumps in distances across continents and great distances where it suddenly becomes established where it wasn't seen before. And this is a function of it taking advantage of ships and planes and vehicles for transportation. So this is something where human behaviors have really dramatically affected the risk of dengue transmission by moving these mosquitoes around. And the most famous example of this is the use tires from one country to another and carrying these desiccation-resistant eggs on these tires and getting them established into other countries. So this is a really famous example of human-mediated behaviors, human-assisted transport of Aedes mosquitoes. Now, I'll give you a little more detailed example and some lessons we learned about dengue in the Solomon Islands and dengue vectors in the Solomon Islands. In all the surveys between 1943 and 1978, the only Aedes vector of dengue that was found in the Solomon Islands was Aedes aegypti. Then in 1980, for the first time, Aedes albopictus was found in surveys in the Solomon Islands. And then between 1997 and 2012, we no longer saw Aedes aegypti. It completely disappeared. We only saw Aedes albopictus. And we used to, when I was a young man and first starting out as studying mosquitoes, we used to talk about that maybe this is a good thing because Aedes albopictus was not thought to be as important as a vector of dengue as Aedes aegypti. And that certainly is true. Aedes aegypti is certainly responsible for the vast majority of dengue cases. But we now know that albopictus is a serious dengue vector, and we have many examples now of outbreaks of dengue where you only have albopictus. So what caused this change in this disappearance of Aedes aegypti? Well, there's two factors. So it's oftentimes seen that when albopictus arrives, aegypti disappears. And there's two theories of why this happened. One of them is that Aedes albopictus outcompetes Aedes aegypti larvae for resources in the larval habitat. So this albopictus is a better competitor, and so it suppresses the aegypti population. The other theory, which was Phil Lunabus in Florida in U.S. published, this was the phenomenon of satirization. Now, I think you recall earlier I said that mosquitoes only mate, female mosquitoes only mate once. And what happens in satirization is that the albopictus males mate with Aedes aegypti females, so that the male albopictus outcompetes the male aegypti for aegypti females. And so, as you recall, we said that the female only mates once. So that after the albopictus male mates with the aegypti female, that female aegypti is no longer able to produce fertile eggs. It will not mate again. So essentially, it's suppressing the aegypti population in that way. So that's one of the ways that we think that albopictus outcompetes Aedes aegypti. So let's go back to the Solomon Islands example again. This is in Honiara in 2012. The survey was done by Charles Butafa as part of his postgraduate studies. And in 84 sites, he only found Aedes albopictus. All the blue spots on Charles's map are where he found Aedes albopictus. The black circles, which are a little bit hard to tell on this map, he didn't find any dengue vectors. So that was 2012. By 2013, 33% of the sites where he found Aedes had Aedes aegypti. So all the places on the map that have red were where he found Aedes aegypti. So this was after about a 35-year period of time with no aegypti present. And suddenly it was present in about 33% in the sites in Honiara. And he also found this in all the provincial capitals across the country. So once it came back, it became really well established. By 2014, over more than half of the sites, if they had Aedes aegypti. So it came back fairly quickly and got very well established. So these sort of distributions, the take-home message, I think, is distributions of vectors change all the time. And that's one of the reasons why it's important to have ongoing mosquito surveillance, ongoing monitoring the mosquito population, because the vectors, the presence or absence of vectors can change really quite rapidly and dramatically. Now, a couple more examples of mosquito invasions. And since we're talking, the audience is primarily from Indonesia, we had Aedes albopictus introduced into the Torres Strait of Australia from Indonesia. We know that by looking at the genetics of the mosquito, and it appears to have been introduced from populations in Indonesia. there's a cordon sanitaire established in the Torres Strait. So it's only in this part of Australia, these few islands off the tip of Cape York have Aedes albopictus. And there's a very active program right now trying to keep albopictus out of the rest of Australia, because we've introduced Wolbachia into a lot of the mosquito populations, and having a second vector come in would render the Australian mainland susceptible to dengue outbreaks again. So that's an important regional change in vector status. But okay, so we've been talking about Aedes, and we talked about how they have desiccation resistant eggs, and that helps them be transported. But mosquito invasions are not just confined to Aedes, and we gave you the example of Indonesia donating a mosquito to Australia. Well, Australia returned the favor, and we were responsible for introducing Anopheles bancrofti from Darwin to New Caledonia. So in that, Anopheles bancrofti is a malaria vector, as I think many of you know, and it was introduced into a region where there were no anophelines prior to this. So we've changed a non-endemic anopheline area into an endemic area, with the potential that we could see malaria transmission now in New Caledonia. And it's now very widespread in New Caledonia. And that's sends something, we'll touch on that too, on the surveillance system and what happens there. So we have bancrofti donated from Australia to New Caledonia. And then going back a little bit in time, during the American War in Vietnam, we had 7 different Anopheles species introduced into Guam. So Guam was a stepping stone for American troops traveling from Vietnam back to America. And we had at least 7 different Anopheline species hitch a ride and become established in Guam. And actually, we saw local transmission of malaria in Guam. So they did New Caledonia one step further. Not only did the mosquitoes get introduced and become established, they also were transmitting malaria locally. So this is an example of mosquito invasions changing the endemic status for malaria in a different part of the world. Now, we talk about detection of mosquitoes. This is some data from Australia, which has a very robust surveillance system at airports and seaports. And we average about 20 introductions of foreign mosquitoes into Australia every year. And for many countries, I think it's important to realize that when we first detect a invasive species, it's oftentimes not at a seaport and airport. It's far away from there. It's already gone through the seaport and the airport, and it's become established elsewhere, and then it's really difficult to do. So all countries are required by the international health regulations from 2005 to undertake mosquito surveillance and control around seaports and airports. But the reality is very few countries can do this really well. And oftentimes what we see on that map of the distribution, we wouldn't have that big map of the distribution of albopictus around the globe if we did a good job at seaports and airports. If mosquitoes are being assisted by humans to get into a country, if we had a good surveillance system, we wouldn't see it getting established elsewhere. But the reality is it's a very hard thing to do. And in a country like Australia, we get at least 20 different examples of foreign mosquitoes detected at seaports and airports. Now, just a couple of 1 or 2 final slides here about mosquito dispersal. And I want to say a little about Anopheles stevensii, which is the only urban malaria parasite, urban malaria vector that we have. And this is some data from the World Health Organization malaria threats map. And the green dots show where we had Anopheles stevensii. So it's a native of India and that part of Asia in 1995. By 2005, you can see it's starting to disperse east and west. And this is quite a different pattern than what we saw with those other maps of albopictus, where we saw large jumps in movement of the mosquitoes or the movement of the anophelines from Vietnam into Guam, which is a distance of thousands of kilometers time. This is a more gradual spread of the mosquito across space. And here in 2023, there's this dot here. It was introduced into Sri Lanka, and now it's going to be quite common across Africa. So this is of great concern because of it's an urban malaria vector. We're seeing large outbreaks of malaria in places like Djibouti, which didn't really have any sort of outbreaks in that scale before. So it's a serious threat to the attempt to control and eliminate malaria. Now, a number of us think that it's a possibility that this isn't human-assisted transport of mosquitoes, and we feel that it could very well be wind-assisted transport of mosquitoes. And part of this is based on the fact that we see this gradual change of mosquitoes across spaces over a number of years. We don't see these dramatic jumps in large distances. They've also looked at the genetics of the mosquitoes, and it seems to be consistent with potentially with wind-borne transportation. Ovi Lehman, who led this study that we published in PNAS, did it previously in Mali, and he showed a transect line in Mali. You get up to 50 million anopheline mosquitoes crossing that transect by windborne. So Toby did a number of experiments where he put weather balloons and he carried up sticky traps up into the air several hundred meters up there and left them up there overnight and then brought them down. And they found that they estimated there were about 50 million mosquitoes crossing that area of space every year. So that's about 10,000 mosquitoes per kilometer per week. So there is certainly a potential, and this has implications for how we do surveillance and control. Because if we only focus on ports and seaports and mosquitoes are getting blown in from elsewhere, then it's really, I think what's basically arguing is there's a need to increase our surveillance everywhere, not just to be overly focused on seaports and airports, which are important to do. But I think we need to strengthen vector surveillance programs everywhere that have the best chance. Now I'd like to talk about a second driver of changes in mosquito behaviors, and that's climate change. And there's a couple of things. People always get angry at me to say in the next comment and whether it impacts mosquito behaviors. That's easy to understand. But the reality is that the impact of climate change, well, that's clear on the mosquito. The impact on malaria transmission is less clear. And part of this is from the fact that we have 41 dominant species of anophelines that transmit malaria. So, and they all have very different behaviors. So sometimes increased rain will increase mosquito populations and therefore increase the vectorial capacity and capacity to get increased in malaria transmission. And sometimes increase in rain will diminish the vector population. So all these things are very difficult to predict. And a number of studies have looked at this and basically found that over the last 100 years, malaria has been steadily declining on a global scale. In some places, but overall there's been a decline in malaria studies. Is that the impact of climate change is too small to really pick up against a backdrop of many other of these drivers of transmission, some of which we'll talk about shortly in this talk, which includes some of the changes that are a function of changes in landscape. Climate, rainfall, temperature is affecting transmission of malaria at a regional level or at a local level. But when we sum it up globally, change we're seeing is actually affecting malaria transmission. Interest to Pak Tri and I. So we've been working together in Kalimantan. So this is the map showing tree cover lost. And you'll see that Indonesia, with all this red, that's commodity-driven deforestation. And so the question is, how is that affecting malaria? And I think you can probably guess what a lot of this red is actually symbolizing. Okay. But let's talk a little bit about vector species richness. So the composition of vectors in the area. And there's some key difference between Africa and Asia. In Africa, we have 7 dominant vector species. They're predominantly indoor biting mosquitoes, and predominantly 6 out of the 7 vectors have larvae that like habitats that are in bright sunshine. So when you undergo deforestation, you're increasing the amount of light, you're increasing larval habitats, and almost invariably, the amount of malaria increases in Africa. Whereas in Asia, it's a much more complex ecology. We have 19 dominant malaria vectors and a number of secondary vectors. A lot of our mosquitoes are what we call outdoor mosquitoes, and their larval habitats can either be in sun or deep shade. So it's really much harder to predict what the impact is. So sometimes deforestation increases malaria, sometimes it decreases malaria, and sometimes it has so it's a much more complex ecology that we have in Asia compared to Africa. Now, one of the things that deforestation has received a lot of focus on and interest in is, and here we see some of the changes in deforestation, which is oil palm plantations being put in. And that's the impact on monkey malaria transmission. I think we mentioned earlier on that monkey malaria, simian malaria parasites in humans is a serious problem. We don't have the long chain transmission from people to mosquito to people to mosquito with monkey malaria parasites in people. But so we only see transmission where we have macaque monkeys, long-tail and pigtail macaques. And this has implications on whether or not countries will be certified as having eliminated malaria. Again, if we have more than 10 human cases in a country, which isn't very much, then the WHO will not certify a country of having eliminated malaria. So the classic example of this is Malaysia, which has no human malaria parasite transmission for the last 3 or 4 years, but it has thousands of simian malaria infected people, and so they will not be certified as having eliminated malaria. And that was a very controversial and spirited debate by the Malaria Policy Advisory Committee when that topic was discussed. So what's the impact of deforestation? And this is some of Pak Tri's data here, which he's kindly allowed me to steal and show to you. And we have various land use types in Kalimantan. So on the left-hand side here, don't worry about trying to read. These are a list of mosquito species present in Kalimantan, or some of them. The red squares indicate where the species is a known human malaria vector. The green is whether or not it's a monkey malaria vector. The blue indicates a dengue vector. So here we have here 1, 2, 3, 4, 5, actually 6. We have 1 mosquito here, balbocensis, which is known as a human and a monkey malaria vector. We have 2 monkey malaria vectors present and 1 dengue vector, albopictus. So when we did surveys in forested areas that hadn't been logged, we picked up 2 mosquito species. Both of them were human malaria vectors. Oddly enough, we didn't see a zoonotic malaria vector. That may be just a function of not our sampling size yet. And we didn't pick up a dengue vector. Now, when the areas were in logged area for us, the number of mosquito species found increased to 12. And we saw that we had Aedes albopictus, which was the dengue vector present. So what we're doing is we're looking at this shift in mosquito distributions as a function of landscape type. And then we're areas where we had mixed agriculture. And by mixed agriculture, we're defining this as areas where they had put in oil palms. So these are young oil palms, and other agricultural crops were put in. And so in the areas of mixed agriculture, we had 24 mosquito species that we found. 2 of these were human malaria vectors. So here and Balbacensis down here. We also found 2 monkey malaria vectors present, and Aedes albopictus, the dengue vector. Then as the oil palm plantations get more mature, if you look at mature oil palm plantations, the number of species was less diverse. Only 7 mosquito species found, 1 of which was a human malaria vector, and also 1, the dengue vector, Aedes albopictus. And finally, if we look at residential areas in the nearby gardens that are with them, we found, it's quite amazing, 40 mosquito species, including 5 human malaria vectors and 1 zoonotic malaria vector, and also Aedes albopictus. So again, we're seeing that the impact of land use change in here in this example in Kalimantan. So we get different mosquitoes compositions in different land use types, and the importance of the risk of transmission of malaria, of human and simian malaria parasites as a function of land use types. This is some data from Sumatra, from northern Sumatra, by 2 students in my group, Bram van der Straat and Bonnie Sabayang. And the point I want to make here is these are 2 Dusun that are in close proximity to each other, Dusun 2 and Dusun 5. Dusun 2 is predominantly a mature oil palm plantation, and we're looking at the abundance of Anopheles dirus group mosquitoes in a small area. Now, these yellow arrows are pointing to these small little dots, which indicates only a few, 1 or 2 Anopheles dirus are found in these areas. So we get very much a negative association with dirus with the mature oil palm plantation. But if we go in Dusun 5, which is where the village is, where residences are, again, we have one sample site here in the village with hard to aim mosquitoes. But within a couple of 100 meters, in areas where there's gardens and mixed vegetation, agricultural crops, very large number of mosquitoes, so a much greater risk of being bitten by Anopheles dirus, which can be a simian malaria vector and a human malaria vector within this small geographic area. So you got different species compositions by habitat types. And then within a habitat type, you have large variations in the risk of being bitten within a small geographic area. Again, the same to do some data for Anopheles maculatus here, which is the opposite. Dirus, as we showed, the mixed agriculture, the garden areas had a very positive association with dirus group mosquitoes and a negative association in the mature oil palm plantations. Maculatus, which is a human malaria vector, very strong positive association with oil palm plantations, and a very strong negative association with the village itself. So again, you got the species distributions vary quite a bit by landscape use, and then we have variations in how many mosquitoes we find within those habitats. Now, I want to say a little bit more, one last thing about land use types, and this is the looking again at the same area, Dusun 2 and Dusun 5 in Langka in Sumatra, and looking at larval habitats. So we can categorize mosquito larval habitats as Natural habitats, things like coconut shells, stream margins, groundwater pools, rock pools, the traditional sort of habitats of these mosquitoes. And we look at how many of these habitats had Anopheles dirus, maculatus, Kochi, and Vegas. And then we have the scenario where we're doing land use change. So we have man-made habitats. And oftentimes when we talk about man-made habitats, we're thinking about small containers made of plastic or metal or rubber or something like that. So from artificial materials. But we can also think about when we move into an area and we change the landscape, we also create habitats from natural materials, but they're man-made. So things like ditches along the side of the road, tire tracks, holes that we dig, fish ponds that we put in. These are all man-made habitats created from natural materials. And this is one way of thinking about how does human activity change the risk of being bitten by mosquitoes. Well, we're creating the production areas for adult mosquitoes in these habitats. And it's interesting, you look at Anopheles dirus here, Bonnie Sabine found 18 of these had 18 of the 124 natural habitats had Anopheles dirus, but there was 28 man-made habitats that were producing dirus. So there's getting a greater potential abundance of dirus in areas where there's human activity. And so that it's a interesting scenario. You don't see the same sort of thing for maculatus. Predominantly, you find the maculatus are taking advantage of the naturally occurring habitats such as stream margins, which dominated that. So again, this is another way of how human activities are changing the distribution of mosquitoes. The fourth driver of changes in mosquito populations is urbanization. Now, traditionally, what we've always said is that as cities grow and increase in size, it increases the risk of dengue, particularly for Aedes aegypti, which is very much a domesticated urban mosquito. And we used to always say that with urbanization, you get a decrease in malaria, but that's really been called into the question for what we showed earlier, and that is the changing distribution of Anopheles stevensii, which is the world's only really urban malaria vector. So that's increasing the risk of malaria as cities grow in size. Now, there's another part of this story we talked about before about how these stevensii may be spreading from the wind. And part of the story also, things we're saying is, before, Saudi Arabia was a natural barrier to the spread of mosquitoes. They got this big desert, but with discovery of oil and the establishment of cities in the desert, we've actually created suitable habitat for Anopheles stevensii. So it's an urban malaria vector. It can be found, the larvae can be found in containers. So if you get mosquitoes being blown by the wind across the desert, and that previously when they would fall out of the air, they would just die on the sand. But now there's cities out there, and it sort of serves as a staging ground potentially for mosquitoes to make it across these deserts and then make it into Africa. So I think it's a theory right now, but the evidence seems to suggest it has some plausibility. Okay, again, this has, as we mentioned earlier, this has implications for surveillance and control and implementing the international health regulation. So again, it's a call for increased mosquito surveillance to pick up these spreading vectors. The fifth driver of changes in vector behaviors is vector control. Now, this slide summarizes the World Health Organization recommended vector control for malaria, which relies predominantly on insecticide-treated nets and indoor residual spraying as the main vector control strategies. with improved housing and larval source management as supplementary measures. Okay, so how does vector control affect mosquito behaviors and mosquito attributes? Now, first of all, these interventions have been highly effective. So the insecticide treated, this is a decrease in Plasmodium falciparum infection prevalence in children 2 to 10 years old in Africa as a function of insecticide treated. Nets. In the dark purple here is the impact of indoor residual spraying. And it shows they've been highly effective. I also want to point out this line up here, which is the counterfactual line. This is the prediction of what malaria, and it goes along with what we were saying earlier about there being a continuous decrease in malaria over the last 100 years. Okay. Now, one of the impacts of insecticide-based vector control is the development of physiological resistance to the insecticide. So this is when the mosquito lands on an insecticide-treated surface and isn't killed. Okay, so it either has increased enzyme levels in the mosquito or increased cuticle. So it's either not absorbing the insecticide or it's able to break down the insecticide. And we see very different sort of things. This will focus in on Africa. The red dots are everywhere that we have confirmed resistance to insecticide in Africa, and virtually everywhere you're seeing insecticide resistance. And again, this isn't really that surprising because we said earlier that the African vectors are predominantly indoor mosquitoes. So we're putting a lot of insecticides inside the houses. There's more opportunity for mosquitoes to encounter these insecticides and develop resistance. And actually, it's not surprising that we see resistance. And actually, I always look at these red dots and I say it's an example of, it's documented proof of the success of the IRS and the ITN programs, because it takes an investment by the mosquito population to overcome resistance. So you got to invest in enzymes and physiological changes, and it's not going to happen unless you're hurting the mosquito population. And so it's sort of proof to my way of thinking that the control program was and is still highly effective. But obviously we have to change insecticide classes or it will fail at some point. In Asia, we see a very different sort of scenario. We see a lot more green dots, which indicates that the mosquito population is susceptible to the insecticide. And the behaviors of our mosquitoes predominantly in Asia are very different from Africa. These are outdoor mosquitoes. They don't really like to enter houses as much. And so increasingly we're seeing, and one of the first places we saw what we call is behavioral resistance was the second place we saw in the world was in the Solomon Islands. It was first shown in Mexico. And that's in which we put insecticides inside the house, and these mosquitoes change their behaviors. They shift from biting throughout the night to biting earlier in the evening, so before people go inside their houses. So they're avoiding contact with the insecticide. And then after insecticide-treated nets were introduced, we saw this shift to increasingly outdoor biting. So the mosquito population shift from biting earlier and going from indoors to outdoors to minimize their potential of contacting the insecticides and nets. So it's a very different scenario. So we're starting in Asia, we're starting out with mosquitoes, which are predominantly outdoor mosquitoes, and we're seeing that behavior again even more extreme. And we're seeing this now as well in Africa, I must say. And one of the things you'll see is people debate whether this is truly behavioral resistance or behavioral resilience. And what this basically means is there a genetic basis to this change in behavior? So if you have resistance, and let's say you spray with DDT inside houses and you see the mosquitoes feeding earlier in the evening, is that change a permanent change? So if you take away the intervention, do you see the mosquitoes continue to bite earlier, or do they revert to feeding inside the house? So if they were to revert, that would be resilience. And And if they continue to bite earlier, that's resistance. So in the example of the Solomon Islands, it is resistance because we stopped spraying DDT decades ago in areas before they put in the insecticide tree nets, and mosquitoes are still biting early in the evening. Now, last couple of slides, and we'll throw it open to questions. I want to say a little bit about what we don't know. A higher level insecticide tree nets into 2020. So just keep this in mind in your as we go forward. So we're seeing after 2000, we're seeing increasing physiological and behavioral resistance to insecticide. So one of the things we were looking at is what happened, if anything, before insecticide treated nets. So after about 2004, we see an increase in insecticide treated nets and indoor residual spraying in Africa. And so what if anything was going on here? And this is and what we saw for the human blood index decrease. The red line is for blood meals on humans indoors. The green lines are blood meals on humans outdoors. And for Phonestis and Gambi, we saw a significant decrease in feeding on humans prior to 2004, prior to the introduction of insecticide-treated nets. And if you look at the proportion of indoor biting, again, Gambi, Phonestis, and Arabiensis all showed a decrease in house entering behavior this year. So there's something else that was driving the change in house entering and biting prior to the introduction of insecticide-based programmatic control in Africa. What this is, we don't really know. There are certain things that we hypothesize could be associated with this, which might include things like the use of untreated bed nets or improvements in houses in Africa, which prevent mosquito entry. So again, this is sort of we know that there are some unknowns driving changes that are acting as vector control, and they're probably related to human activities, but what they are, we don't have any definitive proof. So I just want to leave you now with a couple of key points, and we can then throw it out to questions and discussions. I think the key points that I really want to make is that mosquitoes are nimble and they're always changing. Their distributions, behaviors are dynamic. They're always changing. And therefore, it's important if we want to control the transmission of diseases by vectors is to have ongoing surveillance. And the mode of distribution, whether it's human assisted or if wind-borne is a factor, is going to have impacts on how programmatically we need to do surveillance. We're seeing the impacts of climate change on vectors are really local and regional, and it's going to vary by individual mosquito species. But the global impacts on transmitter at this point are still a bit uncertain. It's certainly, we are seeing floods and we're seeing rainfall patterns that are increasing malaria in certain areas of the world, but overall it's being offset by areas where transmission has been diminishing. For deforestation, we're seeing regional impacts between Africa and Asia. Deforestation making malaria far worse in Africa. Asia is a little bit more uncertain, but there certainly seems to be an association with some of these landscape changes with the increase in monkey malaria transmission to humans. urbanization, we're certainly seeing increasing malaria with Anopheles stevens-sized spread as well as with dengue transmission. And vector control has resulted in changes in resistance and behaviors of mosquitoes. Again, and this sort of indicates that we've had a successful program up till now. And finally, the last thing that we point was that we have other drivers of behavioral change that we don't really know what's driving them. We know they're there, but we don't know what they are. And it just really highlights a lot of things that we don't know yet. So it'll leave it. I'll leave it to the audience members to figure out these other unknowns. Thank you very much. Happy to take questions. Right. Okay. So we have some questions about agricultural development in different ecosystems. And a question about rice paddies and related to Asia. Well, rice paddies wouldn't affect Egypti directly because Egypti really is found in small containers. Which isn't to say that areas where you have more people that they're going to produce some of these other small containers, but the rice paddies themselves will not be affecting dengue vector populations, either Egypti or albopictus. I don't know that much about Papua. I used to live in Papua New Guinea, but I never had the pleasure of visiting Indonesia, Papua. Patri, do you know anything about agriculture in Papua and how it compares to Java and the effects of on mosquito and vector-borne disease?
Yeah, actually, the situation in Papua is different with Java. Sorry, my internet connection is not stable before this, so I cannot hear your talk just a few minutes. Yeah, I just talk about the Papua. The Papua is different with the Indonesia, the Java, and also Sumatra and Kalimantan because of the epidemiological situation is different, and the land composition is also different, and the composition of the species of the mosquito is different because of Papua is more closer to the Australian situation, especially in Papua New Guinea situation than in Java. So that's why the vector control approach should be different, Tom, I think. Yeah. Hello, Tom. Can you hear me?
Yep.
Okay,
yep.
okay. Okay.
Fine.
Yeah.
Yeah.
So, okay. Thank you, Tom, for the a very interesting and insightful presentation today. So I think it's really important to know about the climate change and then also land use change and the some impact of the mosquito invasion and also dispersion in relation with with the vector-borne disease transmission. So I think now we have some time for question and answer, maybe from the audience, from the participant. If the many people from the participant have a question, please raise your hand, or maybe type in the chat box. I will call you. Okay, maybe Miss Reza, can you talk now? Yeah. Okay. Please go ahead, Reza.
Okay, thank you for your time. Good morning, Prof. Tom. I'm Reza. I am from Pest Control. I just want to ask about this kind of mosquito. I just because it's very interesting to me. I just found that there are several type of IDs that I just know it's I get T and albopictus. And what I want to ask is whether the different types of Aedes mosquito will affect the level at which they become dangerous factor. And then the second question is why the Aedes mosquito now change from previously, as I know, it's just being found in clean water such as bathtub and etc. But now I see in the previous slide, it's like just found in coconut shell itself. That's it. Thank you.
Yeah, certainly. I mean, you bring up some good points. I think one of the reasons. Let me talk about a couple of things. Aedes aegypti is responsible for, we believe, for about 90% of the dengue transmission. But there are other mosquitoes that can transmit dengue. The Pacific Islands are really unique in that most of the world has aegypti or aegypti and albopictus. The Pacific Islands have 12 different mosquitoes that are dengue vectors, and they all have slightly different behaviors. And so, for instance, what you do to control a dengue outbreak, if it's driven by albopictus or it's driven by aegypti or both, can be very different, because albopictus is an outdoor mosquito. And what we do in Australia up in the Torres Strait is they do barrier spraying. So they spray residual insecticides on the vegetation under 2 meters high, because then the albopictus doesn't really enter houses as readily as aegypti. Whereas if you were to do that for aegypti, you'd have minimal control of aegypti. So where you have aegypti, you want to spray your insecticide inside the house. If you have albopictus, you want to spray the insecticide outside the house. And if you have both, then you're probably going to focus more on aegypti. And aegypti is generally believed to be the more dangerous dengue vector because it's close to exclusively a human feeder. 90 plus to 95% of the blood meals will be on humans, whereas albopictus tends to feed on whatever is available. So if you have dogs around, or you have, goats or whatever, it's going to feed on those animals as well. I think what we're seeing examples of, like in Honiara, which had in the Solomon Islands, which had this big dengue outbreak in 2013, 2014, which was entirely albopictus at the start of that outbreak. And I think what happened there is that we basically created an urban environment that transformed albopictus into aegypti behaviorally, the vectorial, because there was very few other animals for it to feed on. So it had no choice. It had to feed on humans. So that was one of the things that made aegypti such a dangerous dengue vector, is because if you had people intermixed with animals, it'd find the people and it'd only feed on the people. Whereas albopictus would just feed on whatever it encountered. But then when you have an urban situation where you don't have a lot of other animals, then I've got some mosquito trying to bite me here right now. Then it's basically transformed it into an animal that behaves like aegypti. And I think we're seeing behaviors changing. We used to always say, okay, Aedes were sort of like more clean water, and we talked about aegypti being in artificial containers, metal buckets, disused car tires and stuff like that. And that's certainly true. They are major habitats, but you certainly will find, and I've certainly personally have found Aedes aegypti in tree holes. You still will find them under using because they originally came from the forest, so they have the capacity to take advantage of those natural habitats, and you certainly you certainly see that, and you certainly see sometimes you find Aegypti in very polluted water. So they're changing their behaviors. And if you do a collection of Aedes inside houses, you'll find Aedes aegypti in a number of places in South America, certainly in the Solomon Islands. And I would imagine, and certainly Patri, you found it in your dad in Kalimantan of Albopictus feeding after dark. So the idea of that Aedes have peak feeding, after dawn and just before dark. Yeah, most of them biting quite a bit, but you have this long biting tail that goes off till 10, 11, 12 o'clock at night, where you get feeding. So the behaviors are changing. And again, that's I think the big take home message is that you'll read these stories in the textbooks and they'll say this mosquito does this. Well, it's largely true, but it's evolving, and they're taking advantage of other scenarios that we present to them.
Okay, Riza, is it okay for you?
Yes, thank you very much, Prof.
Okay, thank you. So this is Tom. Maybe if in a chat box, I see Mr. Mujiano asked about the daytime transmission of malaria by certain Anopheles species. Okay, can you read?
Yeah, well, yeah,
Okay.
yeah. We
Yes,
certainly touched on that inadvertently. We touched on that. We're seeing Aedes feeding after dark, indoors and outdoors. I'm not sure if that has anything to do with climate change or not, but it certainly is a factor. It's changing its behavior. Why it's doing that is it may be more of a function of availability of the hosts and where people are. And certainly in Anopheles, we're seeing a lot of examples, certainly in the Pacific, and I imagine in Indonesia and Papua, you're going to see Anopheles ferrate feeding. It's going to be a earlier and earlier, evening feeder. So it's starting at, probably peaking, I would imagine, certainly in Solomons, we would see peak ferrate biting was probably between 6:30 and 8:30. I think we had about 84% of our biting took place before 9 p.m. And I imagine we'll be seeing that if we do similar studies in Papua on Anopheles ferrate. You're seeing it in Africa now. There's a lot of stories coming out about African vectors who were, a lot of them, like Gambian finestus, were always defined as these late night, middle of the night feeding vectors. But now they're changing their behavior, and people are collecting them when it's still light outside. So it's changing. And this may be partly a function of insecticides that we're putting inside houses. So they're starting to feed earlier, and it's, I think a lot of it is driven by vector control that we've been implementing. So they're trying to avoid the insecticides.
Okay, Muji, are you satisfied or something need to clarify? Can you open your mic? Okay. Mr. Muji is okay, and then maybe is there any other question from the audience? Okay, I think we have one person that raised your hand. Okay, please open your mic, Mr. Irisa. Please go ahead.
Hello, good morning, everyone.
Good morning.
Good morning, Professor Tom. I have a question about malaria, because in Indonesia, have a plan to move to capital to Kalimantan as soon as possible. So I want to know how will healthcare infrastructure in Kalimantan can be strengthened to enhance the early detection of malaria knowledge, especially because so many cases are often about malaria knowledge in Kalimantan and also in Sumatra. Thank you very much.
Yeah, this is actually Pak Tree's. I'm just his helper. I'm just his assistant here. But I mean, I think we all talk about null's eye, but I think as we study these and collect these mosquitoes, we're finding a lot of different simian malaria parasites. So it's not just Knowles eye that is the challenge. For the capital city, it's probably going to depend. It's probably going to be stuff like simian malaria parasites. It's probably going to be more an issue of where the macaque monkeys are, because you need those to maintain the transmission cycle. So it may end up being more of a suburban disease. Depends on how well tolerated the macaques will be in the middle of the city. But it certainly is an interesting challenge to put it mildly. And it really highlights, I think, how little we actually know about the vectors of simian malaria parasites in Indonesia. We have some data finding simian malaria parasites, finding Knowles eye in particular in one vector complex that no one's ever reported it before. And we talked about having the dirus group mosquito, and the only person who's described dirus in Sumatra before was Pak Tri on morphology, and now we're finding it in northern Sumatra. So right now we're still at the first steps and basically trying to figure out what mosquitoes are infected with simian malaria parasites, and then trying to understand the risk factors. So that's why we're doing all these studies, collecting mosquitoes in different landscape types to figure out where are the risks, where are the most, what mosquitoes are infected with simian malaria parasites, and where do we find them in abundance? And there's it's going to have to start. Effective control really it needs to be based on understanding the biology of these mosquitoes, and that starts with incriminating them, detecting the parasite in the mosquito, and then figuring out what their behavior, when are they biting, in what habitats are they most abundant, do they enter houses or not? Oftentimes it's part of the challenge in Indonesia, I think, and in much of Asia, is that a lot of our dengue vectors, a lot of our malaria vectors don't like to enter houses. It's just, so we have to do something to control them outside the houses. And right now, when you looked at that slide of WHO recommend interventions, they're all basically, other than larval control, they're all indoor sort of things. And larval control is not easy. When you look for larvae, it's a young man's game. It's a young person's game. My old knees do not like going up and down. And it's really hard to find them. And you got these little pools of water and stuff, and oftentimes transient pools. And how do you find those and treat them? So WHO always said they recommended vector control as a supplement where the larval habitats were few in number, they were accessible, and they were basically permanent. So when you have the transient pools of water where the habitats are changing all the time, the location of what is producing which mosquitoes, those are difficult to treat. And one thing we do know about larval control is that the more you do it, the better you get at it. So when people first start out trying to control larvae, it's really difficult. So it takes a while to understand how to do this effectively. And there's certainly the larval source management, habitat modification is something that was really began in Malaysia and Indonesia, and we know that programmatically they could be highly effective, but it takes dedication to doing that, and it's not easy. It's difficult. Each ecosystem is a little bit different, but it takes an investment of time to figure out how to do that properly.
Thank you.
Okay, thank you, Mrs. Arosa. So I think we have still two more questions in the chat box, Tom's, from Dia and from Anis. Okay. Yeah, okay. From Dia, so is there any correlation between high cases of malaria in human and activities of mining or oil industry in the region? So examine like what's happening in Papua.
Well, unfortunately, as I said, I think I've always wanted to go to Papua. I haven't made it there yet. I have been to Banca though, which is someplace that Patrick knows.
Yeah,
and
yeah,
it's in the environmental impacts of mining is I've took some photographs when I was in the plane landing because it was staggering, and you could just see all these larval habitats that were created from the tin mining in Banca. So, and there's certainly examples from Sri Lanka of gem mining in pits and creating larval habitats that increases the risk of malaria vectors.
Okay. And then for the second question is about related with the question from the Mujanto. Is there different behavior also affected by the role of species complex? Yeah, it's about the species complex terms.
Yeah. Well, yeah, that's of course a species complex, of course, is mosquitoes that we cannot tell apart on morphological characteristics, and certainly they do have unique behavioral differences. Some of them are far more important as vectors of malaria than others. Some of them are, there's differences in what animals they prefer to take blood meals on. There's differences in virtually all of the behaviors. You can just think of each of these species has a unique characteristics, and a lot of these, it's a challenge. It's a challenge of in Asia where you have so many vectors, and in the end, we know a little bit about a lot of them, but we don't know a lot about any one of them, or very few of them. And really, so there's a lot of work to be done, and to figure out what are the vulnerabilities. So ideally, what we want to do is understand the behaviors and then match different interventions that target those particular behaviors where we can impact them. And there's no easy solutions here, particularly when you're talking about mosquitoes that like to be outdoors.
Yeah.
So, things like bed nets and indoor residual spraying are a non-starter, or improved housing when they won't enter houses anyway. That's not really a starter. And a lot of these options that people talk about are depend on changing the human behavior. So you talk about using topical repellents or spatial repellents, and we talk about repellents, they're expensive. They're on a application basis per night, per week, whatever. They're going to cost a lot more money to use those sorts of things. So there's really a need for looking at other interventions and coming up with some novel sort of approaches to how we do this. I mean, the idea of using toxic sugar baits got a lot of interest recently, and there's trials that are going on in Africa, but the dogma there seems to be that they're more likely to be successful in areas that don't have a lot of vegetation. We don't have a lot of competing sugar sources. And when I'm in Kalimantan or Sumatra, all I see is sugar everywhere.
Yeah. It's very interesting. Yeah. Is there any one more question maybe from the student or the audience? Yes, maybe if still have. Okay. So one more question from the Nurfanto. I want to ask again, is Aedes aegypti and Anopheles mosquito population can be monitored through technology? Yes, technology, yes.
Well, I guess it depends. We are monitoring things with technology. I mean, we obviously we have to use polymerase chain reactions to identify our vectors and to detect the sporozoite stage in mosquitoes. There is a need for better technologies to sample the mosquitoes, and we did as student did some studies in Sumatra, and unfortunately the thing that worked the best that was practical to implement was human landing catches, and we all know the problem with human landing catches is you have to work with people. Which means that they're expensive because you got high manpower costs. You have to supervision costs and so on. So we need a different way of catching mosquitoes. But a lot of these sort of techniques that work out haven't been universal. There was a trap that was developed with a specific lure that was tested in Africa and was as effective as attractive to mosquitoes as a human. But when it was tried in Asia, it didn't catch a single mosquito, basically. It was really, they tested in Laos, it didn't catch any mosquito. We tested it in Australia. So we share a lot of the mosquitoes that you have in Papua. We have Anopheles ferrata and Anopheles hinosaur. Didn't catch a single mosquito. And the person who did that study was in the same group that tested it in Laos. So the reality is, I think what we're gonna have to do is we may have to have different lures for different geographic areas for different mosquitoes to get some. But we desperately need a way of. There's something of monkey malaria about what's happening up in the canopy. How can we sample mosquitoes up in the treetops without putting people in a chair, tying people to a treetop? So there's a need for technologies for sampling mosquitoes, and it's somewhat embarrassing to have to admit this after all this time that we're still struggling to catch a lot of these mosquitoes. We're still doing the sorts of things that Ronald Ross did, over 100 years ago to sample our mosquito populations.
Yeah. Okay, and then once more question from Obi. So can Aedes aegypti mosquito larvae live in brackish waters? And then number 2 is about the suggestion for the PhD research on viral vectors. Okay.
Well, I've never caught Aegypti in brackish waters. It's always been freshwater. I've caught it in fairly polluted waters that were really pretty fetid. I've caught them in coconut shells and tree holes where the dogma would say they're not common anymore, but they're adaptable. Suggestions for PhD research on viral vectors. I mean, I think there's still a lot of basic questions on where does transmission occur, and the changing behaviors of Aegypti and albopictus in rural and in urban landscapes. So there's a lot of really basic stuff that there's plenty of scope to do PhD research on.
Yes, I hope the answer from Tom is clear, about the suggestion of your PhD plan. Okay, so I think it's more than one. Yeah, it's about 1 hours and 30 minutes talk. It's very interesting talk, Tom. I think, and many questions from the audience. I think not only from the student, but also from the Ministry of Health, from the research institute, and from the others. So from the pest control, I also saw from Reza is come from the pest control. So I think thank you very much for the great question from the audience. And maybe Tom, do you have any final thoughts of comment before we wrap up? For the
It's been a pleasure. Thank you for the invitation to come and talk to you today. It's been a great pleasure working with Pak Tri and all my collaborators in Indonesia, and I look forward to coming back and seeing you soon.
Yes.
And there's a lot of work to be done. We obviously there's a need for students, postdocs. There's and with the capital changing its location, there's going to be a lot of I think things that we don't know about how that's going to affect the health of the people moving to the new capital. So there's plenty of work to be done. Yeah,
I agree with you. Okay. Thank you all for your participation and engagement question, and which made sessions more dynamic and interactive, I think. So we look forward to welcoming you to our future lecture. Maybe. Thank you very much, Professor Tom Burkot, for your attendance and for your very interesting lecture today. we are very happy with this session, and you know that about more than 120 participants that follow this lecture, and I think more in YouTube maybe after this. So I think it's a great opportunity for us having you, and thank you very much again, and have a great day for everyone. Okay, once again, thank you, Tom, for your valuable time and insight.
Right.
Okay.
Thank you.
Okay,
Bye-bye.
bye-bye, Tom. Okay, thank you very much. Thank you very much, everyone. Bye-bye. Ya,
Terima kasih, Pak Tri.
oke, makasih, Pak Iko.
Terima kasih Pak Tri.
Terima kasih, Pak. Mari.
Terima kasih Pak Triwibowo.
Oh, mari, Mbak Siti, Mbak Alfi.
Terima kasih, Mas.
Mari, Mas. Yuk,
Terima kasih Mas Tri.
monggo, Mas. Terus, sami-sami.